Okay, we've got the four of us. Nick is trying to get back on, so I think he's probably rebooting his computer. So while we're here, I would like you to go to page 97. Okay, so we're going to talk through this. This is the last part of this section, then we're going to talk about what we're going to do. Okay, Nick's on his way back. Is that working, Nick? Do you hear us, Nick? Because we don't hear you. You do hear us? Not if you hear us. You do hear us.
Give it some, okay.
Wow, you got a really bad connection. It seems like you're moving around really slowly. Are you okay?
Yeah, I don't know.
There we go.
There we go. Now we got sound.
Yeah, my headset wasn't working, and maybe the internet's not working well. I don't know.
Well, you're there.
One of those days.
Okay,
Phase of moon, day of week. I have noon.
You're here. We're just missing Bruce, which usually. Anyway, we're on page 97.
Okay.
Clausius-Clapeyron. This is an important equation, and what we're talking about is it's going to be kind of talking about these cycles, but this time we're using latent heats in order to kind of drive this so-called engine. So let's take a look at the second paragraph on 97. Let the working substance in the cylinder of a Carnot heat engine be a liquid in equilibrium with the saturated vapor, and let the initial state of the substance be represented by point A. So we're back to our little diagrams. And so what we're saying is we have got, oh, hey, Bruce, we have got saturation. That's what it means to be at equilibrium. Because remember what we defined as what saturation is? It's an equilibrium between the rates of condensation and the rates of evaporation. And that concept is kind of important, especially as we get into when we start talking about cloud processes, because we're going to see stuff different with ice. In any case, so at point A, the saturation vapor pressure is going to be E sub S minus some incremental change at a cooler temperature. So they could have switched that and they could have said plus DT and plus D E sub S. But nonetheless, so you're going to look at A and B, and you're going to be saying, okay, instead of having pressure on the side, we're going to have saturation vapor pressure on the side. So we're getting to a warmer temperature. We'll go to a higher saturation vapor pressure. Does that make sense? E sub S?
Okay.
The adiabatic compression from state A to state B, so you're compressing it adiabatically, it's going to warm the temperature, and then you place the cylinder on the non-conducting stand and compressing it infinitesimally, right? So that's why it's derivative. Now let the cylinder be placed on the source of heat at temperature T, and let the substance expand isothermally, just like a normal Carnot engine. So if you look at the picture on the next page, in this transformation, the pressure remains constant at E sub S, and the substance passes from state B to C. So we go back to B to C on that diagram, and you're staying at constant saturation vapor pressure as it expands. If the specific volumes of liquid and vapor increase in the volume of the system in passing from state B to state C, also the heat absorbed is the latent heat. So what you're saying is that this change in the capacity is really a change in the actual amount where we're getting condensation or evaporation, whether the heat's positive or negative. So then when you go to equation 3.91, please take a look at equation 391, right? We know those relationships are true. And so we get Q1 minus Q2 is the net heat by the work, right? So I'm going to do this. I'm going to share my screen for a second. Oops. And I'm going to move you here. And I'm going to expand that window so your faces are big and beautiful in my screen, except for Jacob and James, who are black boxes to me. We'll get an Epic pen, and we'll black out the screen, and we'll use green, because I kind of like green.
391 is also equal to 0, right?
Yeah. Well, no. Because Q1 is greater than Q2. So it's not 0.
No, it can't be. It says Q1 over T1 is equal to Q2 over T2.
Right, so that can't be 0. But remember that work is always the change in the heat, right? So when we say that the work is Q1 minus Q2, does that make sense to you? So Q1 minus Q2, that's the heat that we've got going on here.
Why wouldn't these be equal to 0?
Say what, Jim?
Why wouldn't that 391 not be equal to 0?
Because I think
it's the ratios. I'm
right,
sorry.
it's the ratio. So if you did that, right, oops, I'm sorry.
So the ratios are equal to 0.
No, ratio can't be equal to 0.
Well,
this can't be a 0 equation. Then you'd have no heat. Don't remember, this is equal to this, right? So you're not just, don't think that you're just doing this. Is that what you're thinking? Equals 0?
Yeah.
Okay, yeah, but that's not the right-hand side of the equation. You can't just make it over the same, right?
Okay.
So that's, if you go back to 383, they're just saying that the ratio's there. So to get to the right-hand side of the equation, how would you get there? How do you get to the right-hand side of the equation?
Through the product rule?
Well, let's try it. All over T1 minus T2.
Quotient rule, I'm sorry.
You got to get a common denominator. You got to get a common denominator, and then you can do
right. So how
plus and minus.
How would you get there? Right. That's going to be 1 over the difference minus Q2 over the difference, right? And in that case, you'd have to do some funky stuff. Well, what do you think? I know that's what we're all looking at, right?
Yep.
So Bruce, I don't know, are you following along? What we're basically saying is, well, how do you get to this right side? We know that this is, it says from equation 383, that's what this is, the ratios. So how do we get to this? And I would guess probably what I need to do is multiply by T1 minus T2. So let's try that. We get, don't draw with geometric figures. T1 minus T2 times one of these, so let's just try this one, is equal to Q1 minus Q2. right? And then what? Multiply through by T1. Right?
Is that first Q, Q1 on the left-hand side?
Yes. And so you'd multiply, you go T1 Q1 minus T2 Q1 equals T1 Q1 minus Q2 T1. I can get rid of this stuff, get rid of the negative sign, and then I've got the ratios back. So I've just kind of proved this. So this is one of those things where you look at this and you're like, oh, yeah, okay, that's probably right. You just haven't seen that it's done. So does this make sense that I've kind of shown you that 1 equals 1?
Mm-hmm.
Or that I get the ratios back if I divide right here, just finishing up this problem just so everybody sees it. I divide by T1 on both sides. That goes away. Oops. That goes away. And then I divide both sides by T2. And then that goes away. And what am I left with? I'm left with Q1 over T1 equals Q2 over T2. So I've kind of demonstrated that that's the same thing. Because I know that that's true. It's kind of weird, isn't it? So what's the purpose of doing this? Because that's really what you have to ask yourself. And so what I think the author is doing here is they go, well, this is not important. You just got to trust me on this one. Because that's usually what it happens. But what we're saying is that Q1 minus Q2 over T1 minus T2 is work. That's the work that you're doing. So therefore, from figure 3.23, which is over there, which if you look at, that's talking about the work in the diagrams. We substitute into that above thing and we get that the ratio of the latent heat of vaporization to temperature is equal to the changes in the volume, right? That's a change in the volume, which we know is associated with work, times the dE sub s all over this amount dt. So it's hidden in this little thing. Q1 minus Q2 equals BC. What does that mean? I don't even know what that means. This is why I don't teach this section. It's really poorly written. Right? Would you agree that?
Oh, he's saying what's happening. BC is referring to the diagram.
Yeah.
In BC, there's a volume change, and it's described by alpha 2 minus alpha 1.
But that's poorly.
Yeah.
Well, that's a stupid thing to say. It's equals BC. It's a volume change.
Yes.
So that the heat that you're getting is because of latent heat, and that you have the volume change times the change. I'm sorry, not the volume change, but the fact that you've got a heating term as the capacity changes, which because the air is saturated, it's actually a change. Remember this, guys. Well, here, I'm going to do it this way. dW sub s is the same thing as dW when the air is saturated. Or the way that we've always described it in the class is that this is equal to this. In other words, how much water vapor condenses is equal to the amount of water vapor that has to condense when the air is saturated. And they're just saying that the change in the temperature is dT. Then, when we take this and put it into the derivative forms, okay? Then they're saying this. And why is that?
Because there's that alpha 2 is significantly greater than alpha 1.
Because one of them is vapor, one of them is liquid. And obviously, liquid is going to be, I mean, a vapor is going to take a much larger volume for a unit mass than a liquid is. So even though we say it's approximately equal to, it's very, very, very close to being equal to it.
So it's another situation where the alpha 1 is just so utterly small as to be disregarded.
In
Well,
the text,
no, because remember here, keep this in mind, right?
Mm-hmm. Okay, so it's not necessarily small. It's just it's
So, right, I mean,
comparatively small.
it's small by comparison. Remember this concept
There
is
is.
small by. So if this is 100 minus 0.1 on the left side, and then the right side would just be 1 over 100. So on a calculator, this would be 1 over 99.9. This is going to be 0.01. What is 1 over 99.9?
what, where?
I'm just, I'll put 1 divided by is 0.01001, right?
Right.
That's a very small. That's a very small difference. We're talking 10 to the minus fifth. So when you have that, that's all they're saying is that this minus this is much closer to just this, because the volume of a gas is way more than the volume of a liquid. So because alpha 2, look under equation 393, is the specific volume of water vapor that is in equilibrium with liquid water at temperature T. The pressure it exerts at T is E sub S. Therefore, from the ideal gas equation, E sub S times alpha PV equals RT. But they're using the correct values for E sub S instead of pressure. They're using alpha 2, which is the specific volume for the vapor. You're using the ideal gas constant for R, and then T is just there. We substitute in there, and we get this final stage, which looks like this. 1 over E sub S times dE sub S over dt is going to be approximately equal to LV, molecular weight of vapor, or water, divided by 1,000, because it's joules per mole or kilomole, right? R star times the temperature squared. Yes, squared, because you get that extra temperature in the ideal gas law. Over the relative, so that's the convenient form of the Clausius-Clapeyron equation. Over the relatively small change of temperatures of interest in the atmosphere, it can be applied to increasing in incremental form. In other words, we're going to look at delta. We're going to use delta now, because even though there's an exponential relationship, we're talking about small temperatures, small temperature changes. So this relationship, when there's small changes, is very close to being what?
Very close to being 0.
No. Like I'm showing you this diagram. What am I trying to express in there? Bruce, what do you see me doing in there?
Is that like dV? Oh, I'm sorry.
This is an exponential relationship, which is a curve in the capacity versus temperature, right? So we know there's an exponential relationship. If this area, delta T, is small, what I'm saying is this. I've got a curved line in the green, but that's very close to a straight line in the yellow, right? The smaller the delta T, the more close the approximation is that dt and delta t relate to d E sub s versus delta E sub s, right? Because an exponential relationship and a linear relationship are not the same, but the more that I zoom in, the closer they are to being the same. That's why they're using equation 3.96 as a incremental, a delta, as opposed to a differential form, which is instantaneous or infinitesimally small. Then what they're going to do is, and you could take 3.95 and you can integrate it. So you're integrating it from whatever temperature, 273. Why 273? Why 273?
Freezing point of water?
Yeah, because what's going to happen below that point? Are you going to have liquid water?
No.
Nope.
You're going to have ice. Okay, and that's going to give you a different relationship, which we know that E sub s of ice is different than E sub s of liquid water, or liquid water. So we're going from liquid to whatever temperature it is. And we integrate it, LV, MW, R, 1000, those are all constants, and I've just got dt over t squared. So the right-hand side of this equation is going to be dt over t squared, or we could say that's we can say that's t to the minus 2 dt. And what is the integration of that?
Add 1 minus over 2.
Right? So if I'm integrating x squared, I know that's going to be x over 3. No, actually, it's not over 2, is it?
Just the negative.
Oh,
Yeah.
right.
because
Take
it's
away the
the
one.
higher one. So -2 becomes -1 over -1, which is just minus dt. Or it's just minus t evaluated from, whatever, 273 to some value t. So it says alternatively, because E sub s at 273 is 6.11 hectopascals, millibars, right? And is that a number that you know by heart? I think that would be a good one to know, 6.11 millibars. And the latent heat of vapor is that number. All they're doing to get to equation 3.97 is they're calculating. I'm not going to write this down, but if you look at 3.97, they're calculating the values based on 0 degrees Kelvin. 0 degrees Celsius, 273 Kelvin. And that's what the formulas you get. So if I said, what makes that value on the right-hand side bigger? What's the answer to that? Look at the right-hand side of equation 3.97. What makes it larger? This is a little algebraic here.
The smaller t is?
Okay, if you have well, think about that.
Larger
If you have a
t.
smaller t, then the ratio 1 over t becomes larger. And you're taking
Oh,
away
wait.
a larger number, which makes the result smaller. So a larger t says you're taking away a smaller number, which makes the multiplication larger.
Yeah, I should have kept track of that. Negative.
No, it's a weird way of looking at it.
But yeah, I get it. It makes sense.
Now, we do not care that much beyond that, but I do want to look at the purple box. So, Nick, would you read that for me, please?
A liquid is said to boil when it is heated to a temperature that is sufficient to produce copious small bubbles within the liquid. Why do bubbles form at a certain temperature, aka the boiling point, for each liquid? The key to the answer to this question is to realize that if a bubble forms in a liquid, the interior of the bubble contains only the vapor of the liquid.
So think about that for a second. You're boiling water and you have this little bubble of water in it. The only thing allowing the bubble to form is the fact that there is a pressure inside. And what is the pressure inside that bubble? What's inside the bubble, which is just a little box of water? It's nothing but vapor. There's no air, right? I mean, you can get air bubbles, but this is not an air bubble. You're boiling water. This is on the bottom of a pot. Keep going.
Therefore, the pressure inside the bubble is the saturation vapor pressure at the temperature of the liquid. If the saturation vapor pressure is less than the ambient pressure that acts on the liquid, and therefore on the bubble just below the surface of the liquid, bubbles cannot form. But as the temperature increases, the saturation vapor pressure increases. And when the saturation vapor pressure is equal to the ambient pressure, bubbles can form at the surface of the liquid and the liquid boils.
Okay, so in other words, if I've got a pot of water on the stove, and there's my handle, and there's water within the stove, the water bubbles start to form on the top, right? And what is their pressure? Their pressure is going to be equal to that of the surrounding air pressure. Now, can I get bubbles forming on the bottom of this pot?
Eventually?
Yes.
What pressure must they be at?
The air pressure plus the pressure that's being applied by the water.
right? Plus the pressure of the water. Now, just so you know, when we're talking about a pot of water, or if we're talking about the ocean floor of water, the atmosphere is 1 atmosphere of pressure, 1,013.25 millibars. So when would water boil? Well, at the top, when E sub S is equal to 1013.25 millibars, which based on the charts that we see, that E sub S, that is at 100 Celsius. That's what we call a standard atmosphere, 1,013.25 millibars, 100 degrees Celsius. Now, a couple of years ago, this is kind of interesting. A guy did, why is it that a bar, why is the atmosphere not 1,000 millibars? Why is it 1,013.25 millibars? And a lot of it goes back to the fact that we probably did a lot of these experiments above sea level. So it's a really interesting history of where that term comes from. There's a guy from North Central that interviewed me and talked to me about stuff a while back, and he did a complete paper on why it's the values it is. Crazy interesting. It's insane. It just kind of happened this way. So what would the temperature what would it have to be down here if it's under more pressure? E sub S at the bottom is greater than E sub S at the top, right? Because the weight of this water, which means the temperature at the bottom must be greater than the temperature at the top. But that should make sense to you, because what is the water doing as it bubbles? What is the water actually doing?
Changing state.
Phase shifting?
No, isn't it convecting?
Oh,
Right? Water, when you're heating it, is going to start convecting. It's going to move. And so what that is doing is it's redistributing the heat, because the bottom's hotter than the top. Now, I always use in my class, if this is spaghetti sauce, what would you do if it just sat there as spaghetti sauce?
Stir it.
You'd have to stir it to redistribute that heat in here, because the bottom would burn if you didn't stir it.
so
Because
once you
it's
get
definitely hotter.
so once you get a rolling boil going in that pot, then you can assume that ES bottom is equal to ES top?
Well, it's pretty close. And then
Okay.
the question is, well, 1 atmosphere of pressure is equal to how much in terms of water? And the answer is 10 meters. So 10 meters of water is 1 atmosphere of pressure. So you have a pot of water, and if it's a 1 meter pot, that's a big pot of water. Now you're talking about adding an extra approximately 100 millibars. So you're not looking at an extreme amount of pressure when I'm just a few inches of water that I'm boiling. But that does go to show you why I can get bubbles forming on the top, and I don't have what Jim says, a rolling boil. And I think when you cook pasta, you're supposed to get the water really boiling, not just the top, although I don't think it makes that big of a difference. But that's also why these hot bubbles down here, when they get to the top, produce a huge amount of heat, because they're actually warmer. That air coming down there is above the boiling temperature, and then you get condensation very quickly. Anyway, so if you think of this, do you agree that the air is kind of doing the same thing in the boundary layer and at the surface? In the actual atmosphere at the surface, this air is super hot, and it becomes less dense, and so we start to convect. And what kind of convection is when I have the molecular boundary layers getting so hot. What is that called? You remember? You guys remember that?
I remember talking about it. I don't remember that.
Sorry, can you repeat that? I was writing something down.
The sun is heating the ground. The ground, this is the molecular boundary layer.
Okay, thermals?
Well, you get thermals. Those are the bigger things. But what is the air doing when it starts mixing right out of the molecular boundary layer? That's called,
Eddies?
Autoconvection?
remember the lapse rate? Jacob, you remember the lapse rate?
Not off the top of my head, no.
It allows the air to be less dense, and so that density overturns it. But think about this. Why does the air down here overturn? Because the air in the molecular boundary layer is less dense than the air above it. Why does the water turn over? Because what are these bubbles compared to the water above it? They're less dense. They become buoyant. And that's why the bubbles rise to the top. That's a very descriptive, easy thing to say, that those bubbles of vapor are going to be far less dense and they'll rise to the top. They will become, you get buoyant. You're auto-convecting it because you heated it to a certain point. But in the atmosphere, the same thing is occurring, just without the change of state.
Okay, so the ground is superheated through convection, and it then cools at 34 degrees Celsius per kilometer for just like a very small amount of time until it
Very small. And then once you get this little bubble starting, okay, so think about a bubble in water. The little bubbles that form on the bottom that you see early on become larger bubbles as you're really bubbling it. So the question is, these little bubbles that form on the ground start to mix the air. How big are those bubbles of air? How big are the bubbles of buoyancy?
Microscopic?
Well, my answer, Jim, is I don't know.
Oh, okay.
Because remember, air is going to mix in and out of this parcel. It is not a Vegas box. It is
Oh, yeah.
right. So I don't know what it is.
It's an open system.
Sense that there is something in the air that is of a different density than the air around it, and then it goes up. And as it does, we get entrainment, we get Gaussian mixing of that air, and it goes away. So I listened to Rich Thompson talk about what's a parcel. Well, it's somewhere, how big is a parcel? Well, it's somewhere between a bread box and a house or something bigger, right? I don't know how big it is. We don't know how big the parcels are, but we see different ideas of them as they move together, and they've got viscosity, etc. So going back to this paragraph, Nick, continue reading from wherever you left off. Where'd you leave off?
I left off at
How's the temperature?
water boils.
Oh, okay.
Yeah. Water boils at a temperature T sub B such that the saturation vapor pressure at T sub B is equal to the atmospheric or ambient pressure P sub atmos, which gives you the water vapor saturation pressure times T sub B equals the P.
So that would be the temperature, the boiling point.
Yeah, the boiling point. Mm-hmm.
So, and then you can just kind of go on and look at this, but we said that. Do you remember? I think I told you that earlier, this class specifically, right? Water boils at the temperature for which the saturation vapor pressure equals the surrounding air pressure. So if I were to put this into a pot, and cover it so it's a pressure cooker, and I increase the pressure, water doesn't boil because these bubbles can't form because the pressure is too great. So the water keeps absorbing heat until that the vapor pressure goes up. So you're boiling something at a much hotter temperature. And since you're cooking food and water has this high heat capacity, this specific heat, it can transfer a lot of heat to the food and efficiently give heat to the food from the water, especially if the water is at a higher temperature. So we can cook things much more rapidly in a pressure cooker, and a pressure cooker allows for a greater increase in the pressure of that pressure cooker. Now, if the atmosphere is significantly lower than 1 atmosphere, the boiling point will be significantly lower, which we've already talked about.
So it's water boils when the saturation pressure is equal to the
Saturation vapor pressure equals the atmospheric pressure at whatever that temperature is. So because this is a function of T, E sub S is a function of T based on the atmosphere pressure, then because of this graph that we have, right, I don't need to have as high a saturation vapor pressure, which means I don't have to get as high a temperature to get there.
Gotcha.
So do me a favor, Nick, one more thing, you would do a good job. Can you just read the little number 43 on the bottom of the page?
Sure. Let's zoom in here a little bit too so I can read it. If, as in generally the case, the water is in a vessel that is heated from below, the pressure where the bubbles originate is slightly greater than the atmospheric pressure due to the extra pressure exerted by the water above the bubble. Therefore, when the water is boiling steadily, the temperature at the bottom of the vessel will be slightly in excess of the boiling temperature. When the water is heated in a transparent vessel, the first visible sign of bubbling occurs well below the boiling point as trains of small bubbles of dissolved air rise to the surface. Note the solubility of gas in the liquid decreases with increasing temperature. The singing that precedes boiling is due to the collapse of the bubbles of water vapor in the upper part of the vessel. Those vapor bubbles probably form around air bubbles that act as nuclei, which originate in the slightly hotter water near the source of the heat. Nuclei of some sort appear to be necessary for continuing steadily boiling at the temperatures of boiling point. Without nuclei, the water will not begin to boil until it is superheated with respect to the boiling point and the bumping, i.e. delayed boiling, occurs. When bubbles finally form, the vapor pressure in the bubbles is much greater than the ambient pressure, and the bubbles expand explosively as they rise. Chapter 6 will discuss the formation of water drops from the vapor pressure and ice particles from the vapor and liquid phases, both of which require nucleation.
Okay, so go to chapter 6. And well, you know what we can do? We can kind of, I mean, take a look at the science that goes into this stuff. So turn to page 210. The second paragraph under the theory. Work is done in treating the surface area of the droplet. This work may be written as A sigma. interfacial energy between the vapor and the liquid, or the surface energy of the liquid. The student is invited to show that the surface energy of a liquid has the same numerical value as its surface tension. So in other words, there is some idea of holding this bubble, and then it eventually breaks and it releases. So you start getting into a lot different. You understand that this stuff in chapter 6 is going to be a lot different in terms of what the science is, because this is much more dealing with observation and trying to figure out what's going on at the very microphysical level. Now, I'm not going to go through chapter 6 with you, because if you were to take a class in meteorology, you would take an upper level or a graduate level course called microphysics, micrometeorology, where you start dealing with all these equations and all this other stuff. Now, I hope if you go to page 214, I hope that we've done this enough in my curriculum. And my curriculum says we're going to talk about these processes in intro. We also do a pretty good job of dealing with this in 1119, so that you see things twice. So Nick, I know you've taken 1119, but we did that whole, there's a MET-Ed module on precipitation type processes. If you want, I would go there, and I'll tell you why you're going to go there, but that would be something to review again. It's really good. I like that one. I do have lectures on that. If you are interested, I can make it available someplace about that process. But notice that they talk about microstructures of warm clouds, and then they talk about it of cold clouds where there's ice. And just keep looking through this a little bit. So look at page 219, for instance. Again, this is a much higher level, but look at figure 6.12. Now do you see that you've got these large bubbles of air within a cumulus cloud, which is what makes it cauliflower-like. It's not just a plume of air. There's all sorts of microphysical processes of bubbles of air and how they're expanding and how they change this, and you've got thermals, and you've got entrainment, and you've got mixing. The process is way more complex than what we talk about in 1115. If we go to the next page, 220, even looking at a stratocumulus, look at the complexity of that stratocumulus. And then there's some model simulations of how these things work. Extremely nonlinear. Then look at that of warm clouds. And they talk about diffusion. They talk about all sorts of things in there. Then they go, look on page 224. And we have the droplet size. Large drops, small drops, cloud drops, CCN. They talk about collection, which is really what we would call with collision coalescence. Look at figure 6.19 on page 225. Notice that these really small drops, if they're at a certain distance, when they move around a large drop, they're not going to collide. I think in class I talked about how sometimes bugs, if they're big enough, are going to hit your windshield, and the little ones go in the airfoil around your car. That's what's happening with these really small drops. So small drops do not have a high efficiency in colliding, and so they don't grow by collision and coalescence very well. Big drops are much more likely to hit each other, and that's what these pages talk about. Let's go to a couple pages. Let's go to page 228. James, would you read that, please?
228, what's...
Yeah, 6.4.3.
Paragraph 3.
No, 6.4.3. almost the last paragraph.
Okay, there we go. Provided a few drops are large enough to be reasonably effective collectors, i.e. with a radius of greater than 20 UM.
What's that? What's that? How do you say that word? How would you say that?
Micrometers,
You could say micrometers, or you could also say what?
micrometers.
Well, different pronunciation. You could also just say microns.
No, microns.
Like,
Right? A micron is a micrometer.
okay.
Less than 20 microns, and the cloud is deep enough that contains sufficient liquid water. The equations derived earlier for growth by continuous collection indicate that the raindrops should grow within a reasonable time periods, around 1 hour. See exercise 6.23, and that deep clouds with strong updrafts should produce rain quicker than shallower clouds with weak updrafts. We have seen in section 6.4.1 that growth by condensation slows appreciably as a droplet approaches 10 micrometers in radius, figure 6.16. Also, growth by condensation alone in a homogeneous cloud and a uniform updraft tends to produce a mono-dispersed droplet.
Mono-dispersed. So,
Dispersed.
in other words, right, there is something in meteorology that we call about drop size distribution. Drop size distribution says, what are the size of the drops, raindrops within a cloud, right? In fact, when I'm using radar, do you remember what the relationship between radar reflectivity is and drop size?
It was in micrometers, wasn't it?
Yeah, what was that? Do you remember?
I almost remember.
Jacob, you remember?
I do not know.
Oh, boo. Remember this? The reflectivity is proportional to the diameter of the sixth. Big drops reflect a lot more than little drops.
Yeah.
To the sixth power by doubling the diameter. Right? So in other words, when a radar is looking at a beam and it sees a sector of the atmosphere, and it's a three-dimensional sector because it's a
I remember that now.
conic shaped thing, right? There is a volume within here. And within that volume are raindrops. And the raindrops are all different sizes. So we need to know something about what is the expected drop size distribution. So that we know what that is going to give us. Now, obviously, if they were all small drops or all large drops, I would get different reflectivities. But what about the rainfall rates? Do you, sorry, not rains, rainfall rates. That there is a relationship between reflectivity and rainfall rate. And that relationship is questionable, and it depends on what type of drop size distribution we have. Okay, so when you're looking at a radar going, how much rain is falling? Do you understand there are approximations saying, this is what I'm getting with reflectivity, this is the kind of environment I've got, therefore there's the rainfall rate. I have to come up with the formula to determine this. In a warm environment versus a cold environment, those are different rates. Warm environments, tropical environments, very high freezing levels are going to be different rainfall rates that we've got to come up with. So when we look at the programs that talk about rainfall, 1 hour, 3 hour collected rainfall, do you understand those are just estimates of how much rain is falling? Because we don't really know how much rain is falling, because we have to know something about what's the correlation between the reflectivity and the rainfall rates.
Oh, it's just a statistical model?
Well, there's different models, and it's actually pretty funny because they have, by the way, Jim, you're hilarious. Do you see Jim in there? Jim's head's gone. If he leans back just enough, all of a sudden your head is pretty funny. A lot of it depends on the drop size distribution. So what you just read here, it says, where were you? And uniform updraft. So it says, in growth by condensation alone, in a homogeneous cloud and a uniform updraft tends to produce monodispersed droplet size distribution. Okay, well, what that tells me is that my drop size distribution is not all over the place. I tend to get all drops of the same size. Why? Because these drops are growing by condensation, not by collision and coalescence, not by ice nucleation. So when I have that, I tend to get much more small drops of drizzle. And then consequently, there have been considerable interest in the origin of a few larger drops. So if you start to get large drops, you start to get different ideas. Then they talk about, well, what about if I have big condensation nuclei, giant aerosols like salt? Would you agree that meteorology, as you get into things, has a lot more details that are far more interesting? Now, as a forecaster, would any of you care about any of this stuff?
Probably not.
When you look at a radar, you go, how much rain is falling? You're just assuming that it's telling you something close to accurate, but it's not always. And a good meteorologist knows where it's going to fall apart. So then we kind of go up and then look at here, 6.24. There's a statistical model for drop size distribution. Because big drops tend to blow apart and form two smaller drops. So the bigger the drop, the less percentage of that cloud is going to be of these big drops. That's because water droplets break apart due to air resistance. So what keeps them from breaking apart? Instead of having a drop, what if we had a hailstone?
How much of it's...
So if I have a big hailstone, that hailstone is not going to fall apart because it's windy. So now I've got really large drops that are going to mess up this whole distribution. So what happens if I start getting hail within a raindrop within a sampling space to the rainfall rates if I'm getting super high reflectivity? What do you think? Nick, do you understand the question I'm asking?
You're asking for at least what it's going to be reflected in the rainfall rate?
Right, so imagine that within this sampling space, I get some hailstones.
Mm-hmm.
What's going to happen to reflectivity?
It's going to go up.
What's going to happen to the rainfall rate?
It's going to have to go up too.
Well, no.
No, it's going to go down.
It's going to go down.
Mm.
So when I get hail, I get these high reflectivities. Now, if I have an algorithm that says, well, the higher the reflectivity, the more the rain, and I'm not accounting for the fact that there's hail, then my rainfall rates are going to be wrong.
Mm-hmm.
I'm going to say, oh, it's raining a lot, and it's not raining a lot. It's just got hail in it, which is highly reflective. So I've got to account for, and again, what I'm trying to, and maybe you don't understand this yet, this is an algorithm that you tell the computer, this reflectivity changes the rainfall.
Mm-hmm.
So let me do this. Let me go here. Reflectivity to rainfall rate. Let's just see what we can do there.
I guess that would physically make sense. The radar would kind of look at it as maybe a higher rainfall rate, but in reality it's not. That's what you're saying, right?
Yes, that is what I'm saying.
Okay.
Okay, so there are certain, as early as 1947, paper published by Marshall et al. Attempted to address the problem by correlating radar reflectivity values, Z, with rainfall rates, R. So we called those ZR relationships. There are certain situations where the relationship does not hold. One example was during Tropical Storm Josephine. The default ZR relationship was used during this event, causing the WSR-88D to severely underestimate rainfall totals across Florida and South Georgia. Tropical storms tend not to have that same curve because they're small drops. And small drops can rain a lot. They're not going to return a lot. So in here, they give you some idea of what it actually looks like. So there's a paper on that. Let's take a look at 1969. Let's not go back that far. Although that's where a lot of it did. So actually, next rad build 10.
You looking for the build notes?
Yeah. What build are we in? Are we in build 10 or build 11?
I think 11's on
Build.
due to be released or has been released. You're close.
Did I look at this?
There you go.
Oh, we're at build 19?
Oh,
I don't know what this is. There's a lot of stuff going on. I don't know what that is. I'm not sure that this is really what I'm looking for. What operational build next rad? Let's see what this is. There's the history of NextRad. How about that? Build 18 deployed. So we're in build 18. Oh, no wonder I couldn't maybe find it. So just so you know, this is all going on behind the scenes to make our radar better. You don't see it. They just upgrade the software to fix things. So let's see if we can find build 18.
but more than fixings, it features.
And add features and dual pole and software that's better, rainfall, ZR relationships.
Build 18.2 beta
Where is that?
toward the bottom.
Facebook, really? Oh, God.
No, that's the deployment.
What I want is a build 8. Oh, you know what I need? Welcome to the world of meteorology. I didn't really want to get into this too much. Here they talked about sales. You guys remember what sales is?
No.
No.
Sales is the fact that they do scans and then they do the lower scan before they do the upper half. So instead of doing every 5 minutes.
Oh, that's the
Do
fast
the
scan.
lowest scan, go to the middle of the storm, come back down to the lowest, then go back up to the top half. So you're getting the lowest scan in the Doppler twice every 5 minutes. So our temporal resolution at the surface is only 2.5 minutes. That was done by a build. That's the computer running the radar. It doesn't change the structure of the radar itself. So here's something, mitigation range folding. You guys remember what range folding is?
Mm-hmm.
And they changed that by the PRF. Auto PRF storm is useful when embedding severe convection is present within a tropical cyclone. They have ABSET, produces faster volume scan updates. Here's sales. Inserts up to 3 supplemental scans of the lower elevation cut in each volume when enabled. Here's the VCPs it goes to. So all these things are part of the build. Here's an MDA algorithm. Remember that? Here, ZDR equation.
Huh.
So what do you think affects the ZDR?
The size of the particles.
And you better know the particle type and the size, right? So what does that is the hydrometeor classification scheme. Remember it says we think it's big drops? That's a really big part of research. The maximum reflectivity value for QPE is 53. Okay, so what they're saying is that in this algorithm, 53 dBZs will be the highest that they put into that formula. So if I'm getting hail at 70 dBZs, I'm not going to do, that's not going to affect it. So I have to take that out. But they allow you to say, well, wait a second, maybe I want to push this number higher during heavy rainfall and tropical cyclone events. So I can change that threshold and actually get more precipitation, a better estimate. So why am I spending time doing all of this stuff? Because I think it's important that you see, it's for you, young guys who are going into the field, what are the options that you could do? Maybe you're interested in radar. Well, there's people developing these things, these programs, because it's not stagnant. Our Doppler radar, our instrumentation system is not the same every year. It's always being upgraded. There's always modifications as we learn and get better. The foundations are the same. The technicalities are considerably different. Last thing, go to page 232, etc. And looking at drop size and particle definition of cold clouds with super and glaciated and mixed phase and homogeneous nucleation and heterogeneous nucleation. You might need to look at those pages again, deposition nuclei, and then you look at graphs so that you know that it's not a simple relationship, it is pretty complex. What I like about this chapter is the complexity is so great, makes you understand how difficult science is. I like theoretical big picture stuff. The details are where people live and work. Look at page 238. Tell me if that's not a cool picture.
It's
The
pretty
growth
cool.
of an ice crystal at the expense of surrounding supercooled water drops. Now, remember we did that in our classes for intro when we talked about the Bergeron process? Look at that picture. Is that not cool?
Well, it must be pretty cool for it to freeze.
It's super cool, right? And then we go to 240, 241, talk about crystal habits, which that is a term that we use in 1119. That is in that meta module. Talk about habits. Look at hailstone formation. Look at page 244 and 245, a couple of cool pictures. So here we have sort of a vertically pointing radar. We see the bright banding. Do you see that bright band there at about 2 kilometers?
Mm-hmm.
We get the way the rain is falling, which I think is amazing to look at. You look at Doppler fall speeds for different hail, and look at how complex this situation is on 6.46. Then there's a little section on modification of clouds. On page 247, there's a whole section on description of what plates are, columns, needles. You talked about hole punch clouds. Look at page 251. Here. Jacob, would you read that second paragraph on in the case?
Where at?
In the purple box, this second paragraph.
251.
251. In case of formation.
Are you there?
Yeah.
Yeah.
6.4.
Yeah, the second paragraph though.
In the case of formation by an aircraft, the ice particles responsible for the evaporation of the supercooled droplets are produced by the rapid expansion and concomitant cooling of air in the vortices produced in the wake of an aircraft, so-called aircraft-produced ice particles, or APIPs. If the air is cooled below about -40 degrees C, the ice particles are produced by homogeneous nucleation. With somewhat less but still significant cooling, the ice crystals may be nucleated heterogeneously. The crystals so produced are initially quite small and uniform in size, but they subsequently grow fairly uniformly. Grow fairly uniformly at the expense of the supercooled droplets in the cloud. The time interval between an aircraft penetrating a supercooled cloud and the visible appearance of a clear air is around 10 to 20 minutes.
So you have a plane that goes through there, creates these vortices on the wingtips, okay, or in the wake of the aircraft. And there's an expansion. That expansion results in cooling. The cooling takes the water that's in those alto cumulus clouds, freezes them when they get down, and really you can freeze at about -35 to -40. So when you do that, if you can get enough cooling due to the expansion, you're going to get ice particles. Well, once those ice particles are created, just like we saw with that ice crystal, now you're going to get the water, super cold water around it, collecting onto the ice crystals. And it says the time between an aircraft penetrating a supercool cloud and the visible appearance of clear air is about 10 to 20 minutes. So you get the hole punch clouds, which are pretty amazing, and people talk about that all the time. And you get this nice big circular stuff because that's where the stuff has happened. They're most likely at low ambient temperatures when an aircraft is flown at maximum power, but with gear and flaps extended, which would be near takeoff or landing. This results in a relatively low airspeed and high drag. Not all aircraft produce them. The shape of the hole in the cloud depends on the angle of interception of the fall streak or the aircraft flight path through the cloud. For example, if the aircraft descends steeply through a cloud, it will produce a nearly circular hole. But if the aircraft flies nearly horizontally through a cloud, it will produce a linear track, like it did in the bottom picture. Okay, so people talk about this all the time. Now you know that page 251 if you want to just talk about it to somebody. Because people will say, this is crazy, this is like government stuff. And you can go, now here's what it is. Isn't that pretty cool?
Mm-hmm.
The next page talks about thunderstorm electrification, which we're not going to do. But again, a lot of stuff you could do on that. and then we get to the end of chapter 6. So I'm not going to worry about that. Let's go back for a second. Go to page, let's go to chapter 4, page 113.
All right. There we go.
I'd love to go through everything and teach you everything and give you a complete bachelor's degree, but I can't. Here they're talking about the spectromagnetic, the electromagnetic spectrum, the spectrum of electromagnetic radiation. There's some really great stuff on pages 114 and 115. This is where Ron's really good. Then, if you skip a little bit more, where we're talking about arc length, if we skip over to page 117 to talk about black body radiation, I've given you my definition, which actually came from the original version of this book, which I think was better. You talk about Planck's function, which is this nasty looking equation.
Nah, not really.
But I want you to see that equation, okay? So C is a constant, C1, C2 are just constants. Lambda, what is lambda?
Wavelength.
What is E? It's just E, right? So the question on the right is, can anything, what's the only variable, or, well, two variables on the right side? What are the only two variables on the right-hand side of the equation?
Lambda and T.
Can any of those make the right-hand side go to 0? Right? 0 can never happen.
Yeah, it's absolute 0, but you can't get there from here.
Well, now even if it's absolute 0, it doesn't go to 0, does it? Because it's E2 something?
Oh,
E to 0 is
Yeah.
1. 1
yeah,
minus
it's
1.
1.
1 minus 1 would be undefined.
Right.
Mhm.
But that's at absolute 0. So when you plot out a black body function, you have a graph that never goes to 0.
Right.
So again, looking at 4.6, do you understand that's Planck's black body distribution? And that will never go to 0. And that's why we graph that logarithmically, because we just keep zooming into the left side. We get closer and closer to 0, never get to 0. And we get this function. And remember, what is the peak of that curve? What is the peak of that curve? I just want to review for you guys.
Spectrum?
When I have Planck's black body distribution, what is that peak called?
Highest intensity?
Spectrum.
No.
Lambda max? Remember?
No.
And then
Max.
what's the area underneath this curve? E star, irradiance.
I always overcomplicate these things.
So we turn to the next page and we go to equation 4.11. What is 4.11? What's that
Wien's
called?
displacement law?
Wien's displacement law, right? 2897. Some people say 2898. It's funny. I don't know what the actual number is. I don't know why the numbers are different. And then we get equation 412. Here they're now saying F, which they're calling the flux density or the irradiance, which some people call I, and I used to call E star because that was the old book that had E star. I don't know who changed it and who does that. I'm not in the science, so I don't know. But that's Stefan Boltzmann law. Watts per meter squared per Kelvin. And then there's some really cool stuff talking about how we get certain temperatures. Look at page 120. The temperature of our Earth, based on the amount of radiation we get from the sun, and this is actually a really good problem. Maybe we should have done this. The sun gives off radiation. It intersects us as a part of the large solar sphere of radiation coming at you. The Earth is a cross-section where we take that cross-sectional area and fold it around the planet. So the equator is getting more intensity, and around the curve, it's getting less intensity. And then you're able to say, well, based on the Earth getting that amount of radiation, what does it have to give off? And it comes up with 255 Kelvin. So 255 Kelvin is the effective black body temperature of the Earth. Is that the actual temperature of the Earth? Is it below freezing? What's the temperature of the Earth?
$255?
No, remember it's 15 degrees C, which is 288.
No, 288. Okay.
So the actual temperature of the Earth. Why is it this?
But when we say the actual temperature of the Earth, what exactly do we mean by that? Like the crust, the core, like what part of the Earth are we talking about?
No, this is, okay, what we're saying, in order to have radiative equilibrium, that is the temperature of the Earth that we need to account for the radiation coming in. Why is the actual average temperature of the Earth 288?
Because not all the radiation is, some of the radiation it absorbs, other is irradiated back out into space.
Yeah, but what's this called? What's the process called?
Oh.
That's the greenhouse effect. The Earth's temperature without greenhouse gases would be 255 Kelvin. Good luck getting life. It's 288 because of the greenhouse effect.
Okay.
Because, and remember, this is what I've been teaching in my classes, I think a lot better now than I used to even in the past, is what is our source of energy?
The sun.
And the atmosphere. So when I'm sitting here on the Earth, I get sunlight. That's a source of energy. The atmosphere is a huge source of energy. It brings our temperature. If without the atmosphere, our temperature at the surface would be 255. With the atmosphere, our temperature is 33 degrees Celsius warmer. On average, 59 Fahrenheit. So we are getting energy from the atmosphere. The greenhouse effect is not annoying. It's mandatory for life. And if you talk about climate change with anybody, I think that's one of the first things you need to make sure they understand.
The greenhouse effect is necessary?
It is necessary. You would die without it. Okay. Kirchhoff's law, I think I want you to know that. Just says the energy coming in, if something is a good absorber, it's also a good emitter of radiation.
How do you spell Kirchhoff there?
Page 121.
Oh, there it is. That okay. So small on the top of the dang page.
What was your comment about Kirchhoff's law? You said a good.
If something emits radiation well, it absorbs it well. So an object is a good radiator and absorption at those wavelengths. So in other words, water vapor absorbs infrared radiation. It also radiates infrared radiation, which is why the satellite can look at water vapor and see types of radiation, because that's what it's able to absorb. Something I just found out the other day, and I didn't know this. The greenhouse effect, greenhouse gases, have to be at least triatomic, not diatomic. What are the two most abundant gases in the atmosphere?
CO2?
No, two most abundant gases in the atmosphere?
O2 and N2.
Right?
O2.
Nitrogen, oxygen.
Oxygen.
The atmosphere is mostly diatomic. If those were the gases of our atmosphere, we would not have the greenhouse effect. So we need to bring in triatomic gases. So what triatomic gases exist in the atmosphere?
CO2?
CO2,
O3?
O3,
Could you count
Probably.
H2O too? Or H2O?
H2O is water
right?
vapor.
Water.
Yeah.
Those are triatomic. Now you also have methane, which is pentatomic, but I'm assuming it's more than that. But just nitrogen and oxygen and argon would not be good. We need water and ozone, and although ozone's not that much, but we need water and CO2. Those are really important greenhouse gases. So I just found that out. So we go on, we can look at page 122, 123, talk about absorption, we talk about scattering. Look at this, see that page on 123, the diagram, figure 4.11? It talks about the regimes of Mies scattering, geometric optics, and Rayleigh scattering. Mies scattering is the annoying one, but that's the one that's really important for light. We go to the next page. Now we start getting into atmospheric optics. We go to page 127. We're now talking about absorption, which I could stand to know a whole lot more about. We go to Beer's law on page 130, which I'm not going to deal with. But that has to do with satellites. Skip ahead. Look at something like this. Look at page 141. Now we're talking about how you absorb certain types of spectrum. Look at the most complex one in the middle. Water. Water vapor is crazy important in terms of radiation transfer. And then we get to the end of chapter 4. And then we look over here, chapter 5, atmospheric chemistry. I'm not even going to look at, but obviously that's important. And then go all the way to page 271. And now we go into atmospheric dynamics, and this is where we start. So we're going to focus. So we've done everything up to chapter 7 as far as what we're going to do in class. Now, let me show you something here, guys.
Paul, do you know the RPG code is available?
What'd you say?
The RPG code is available?
Oh, is it really?
Yeah, I've got a copy.
So go to your Blackboard. That's cool, Jim.
Blackboard.
And go to our class. And go to assignments. No, go to the syllabus. And I want to show you that we have this wait, Am I missing something? Yeah, I think this is it. Have I told you about the big project that's due?
No.
Nope.
Nope.
You're going to hate me at first, but then you're going to love me. So let me go here for a second. I can't find it. Okay, I will post this later. So what we are doing is this. We have a big end of the semester project where every student who leaves COD meteorology ought to know these things. Bruce, this is going to be right up your alley. I think you're actually going to do well on this. And you need to write about all of these things that everyone needs to know. And it's a project, and I've had people turn it in, and when they turn it in, it's the best thing I've ever seen. We're talking over 100 pages of information, diagrams, notes. And that is the project that you're going to do, is you're going to put together. And some of them may be something straightforward as discuss all the cloud types. Some of them will be what is derived Poisson's equation, defining the terms, things that we've done in class. Some of them are going to be things you'll do independently. Some of them are the things that we've talked about in class. I think that that is going to be the most valuable thing that you do. So Jim, Bruce, I know you guys do stuff like this. This is your huge project. But I don't want to give tests. I'm kind of done with that for you guys. I don't want to do that in this era. I don't want to do that this semester. So I am not going to give you a test. But this will be, the project will be, your entire grade is based on that for the most part. Now I do want you to turn in your problems. They're due by Thursday. Because we've talked about this. So I put that as an assignment online. I will put this final project workbook, but we're talking about each little topic from here on out. You should be able to write some paragraphs on. Some of the stuff is coming out of the first unit, so you're going to have to put that in there, and you've been doing your notes. So it's the quality of the information you put down. I'm not going to give you a test and show me that you can do this. I'll see if you can do the problems. I will see how you write up derivations, how your notes are showing me all the steps. But I'm not going to give you a test. Because I would give you an open no test, and if I'm giving you an open no test, then you'd be writing what I'm asking you to write in the first place.
Okay, so for the project, we're gonna have a rubric, I assume, up soon, right?
Yes, I will get that in the next couple of days. But that is what it's going to be. So we are now done with Unit 2, which is everything we've done up through Chapter 6. I mean, we skimmed over the stuff because this is just a review of things, but I wanted you to see it. Now we start dynamics, and this is the totally different field than thermodynamics. But it'll be fun. So is that fair enough? So Mike, if you're watching this on recording, I am not going to be taking from you a test. You're not going to have 2 hours to complete a test or something. Unless you want that.
I hate open book tests.
I started thinking about people like you, Bruce, and I thought, you know what? This is something that you're going to put together this great set of notes for your own edification. For James and Jacob and Nick, you guys are going to have a set of notes for your career. And like I said, I've had people well up in the 100 pages. Margot, I mean, they're amazing. I can't even tell you how great they have been. So I'm expecting that kind of great things from you, and that's what your grade will be based on. But I want you to take this course and go, this is what I know. I know this, and I'm good at it.
Did you used to assign this with exams in the past?
Yes, I've always had this with exams, but my exams were classroom exams, so people had to study. And now, since I'm not going to give a classroom exam, and it would be open notes, there's really not a purpose to it. You guys have shown yourself to be here all the time doing your work, so I will grade your problems based on that quality. On Thursday, we will go through the problems as there's issues with some of them, but I want to see the work that you do. So they're due by Wednesday night at midnight.
All right.
That's where you're
All right.
turning them in. So that's on the assignment sheet. Okay? That is the end of class today, guys.
Thank you.
All right.
I think this will be worthwhile for you. That project will be something really you should be proud of.
Cool.
Okay? All right, guys. Peace out.
Take care,
All
Paul.
All right.
See you
Bye-bye.
later.
See you Thursday.